All right, well now let's go back to a conducting tube again, or a cylinder. This time it's hollow, but it's a thick-walled cylinder. And we're going to also have a line of charge going right through the center of positive lambda. And positive lambda is also the linear charge density that the entire tube itself has. So there's two linear charge densities here of lambda, the line of charge and the hollow tube itself. So we're going to figure out the E field in all of space and then the charge densities of the inner and outer surfaces of this tube. Lambda is Q over L, or Q is equal to lambda L. Keep that in mind. We have radii A and B. Now for R less than A, here's a Gaussian surface, believe it or not. And so I know it looks like it's on the outside of this thing, but it's not. It's on the inside. And it's contained within this material. And it's the best I could do in PowerPoint. It doesn't lend itself to such a fantastic visualization for something like this. So it's the Gaussian surface is also of length L, as we did before. And then the flux, integral of E dot dA, E times A, the area of the Gaussian surface, 2 pi r L, 2 pi r circumference times the length is the area, is Q enclosed over epsilon 0. Well, what does it enclose? Well, it encloses this lambda of linear charge, this line of charge going through the center. So E is equal to lambda L over epsilon 0 A, 2 pi r L epsilon 0. And so the E field is lambda over 2 pi r epsilon 0. That's for R less than A. Now between A and B, the E field is 0 because we're in the conducting material itself. And now for R greater than B, E is equal to Q enclosed over epsilon 0 A. Q enclosed is twice lambda L. There's two lambdas to enclose, so to speak. Or you could just say the entire lambda is double. Epsilon 0A, 2 pi r L, cancellations, the electric field outside, lambda over pi r epsilon 0. Now the surface charge on the inner surface, recognize that if we have a Gaussian surface going through that, the material of the hollow tube itself, it has to enclose no charge. Therefore, the inner surface has to have the opposite of the charge of the line of charge, which would make it minus lambda. The outer is outside of the hollow tube. You're enclosing the entire system of 2 lambda L. I'm sorry, 2 lambda. So that's what the surface charge per lengths look like. Now let's graph it, graph the E field. So between 0 and A, we have the value at A of lambda over 2 pi epsilon 0 A. R is A at that point. And then we have 0. And then at B, we are enclosing twice the linear charge density. So depending on what the relative values of an A and B are, we might spike up over the value that it ends up here. Depends on these values, of course. And then inverse R again after that. So there's the value at B, and it continues on down. Well, here's an example of something we've already covered. The difference between a plate and a sheet and the E field produced. So let's consider this again. What's the E field from a plate? How does it compare to a sheet? A sheet, we have surface charge density sigma. We put a Gaussian surface through it, and the E field is coming right through the area of the end of this little cylinder Gaussian surface. We're plunging through the sheet, so that's where the electric field is, and it comes out on both sides. So sigma is Q enclosed over epsilon 0. Well, sigma is twice EA. And that's Q enclosed. Well, the charge enclosed is sigma times A. And so we have our answer. E is sigma over 2 epsilon 0 from a sheet. A plate, it's a thick sheet, right? So it's kind of like two sheets. The charge is distributed around the whole thing. It's actually not uniform at these corners, but I'm not worried about that right now. So I'll give a couple options here in terms of how to analyze this. We'll stick a Gaussian surface of one is in the plate. We've already done this. Then we have an E field coming out the right side, and that's it. The flux is Q enclosed over epsilon 0. EA is the flux. Q enclosed. The only thing it's enclosing is this charge, which is sigma A over epsilon 0, gives us sigma over epsilon 0. And we could do it in this manner. We could take a Gaussian surface through the entire plate. Then we have twice EA for the flux. Electric field coming out both sides. So 2EA is 2 sigma. It's enclosing twice the charge that it did over here. So this analysis began the same, but the Gaussian surface is only enclosing 1 sigma A. Here it's 2 sigma A. And so the 2's and the A's go away, and we get sigma over epsilon 0. In this little example, we have a slab of material and a coordinate system here. The material as dimensions is given. We got surfaces 1 and 2. We're going to figure out the electric flux through those surfaces. Well, the electric field is in the x direction. It's 250 nanocoulombs at x is equal to 0. And it's parallel to the x-axis. Depends on x, independent of y and z. So the E field is in this direction and x dependent, but y and z have nothing to do with it. So there's the E field through surface 1. E in the x is a function of x. EY is EZ, 0. Now, through surface 1, the electric field at x0 is just 250 nanocoulombs. So the flux is EA, 250 times the area, which is just 2 times 3, and that gives us 1500 Newton meters squared per coulomb. Surface 2, that should be just obvious. The flux is 0, no electric field through that surface. Let's now consider that this slab is just part of a much larger slab of insulated material. And there's 36.6 nanocoulombs within this volume here. And so the goal is to figure out the vector electric field on the opposite side of surface 1. Let's let the Gaussian surface be the entire slab volume, the surface of this material. Then the electric flux is Q enclosed over epsilon 0. And that is Q over epsilon 0, namely the 36.6 nanocoulombs. That's what's enclosed. Well, the flux is already known. We know what the flux is through surface 1. It's 1500. And then in addition to that, we have EA of the opposite side, the electric field times the area. The area, of course, is 2 times 3, which is 6. So let's solve for the electric field. We do the algebra. We subtract 1500 from this, and then divide by A. So there is Q over epsilon 0 minus 1500 times 1 over A, which is 1 over 6 times Q, epsilon 0, and then minus 1500. Which gives us positive 440 newtons per coulomb. Now, that may not seem very astounding. Question, though, is it possible for this electric field to be produced entirely by the distribution of charges within this slab? And the answer is that part of the field must be external, since the field is uniform. We have a uniform field, and uniform fields are only produced by infinite charge distributions, not by finite charge distributions. Well, that will conclude our basic introduction and analysis of Gauss's law.